Stochastic Modeling of Post-Stroke Memory Recovery, Using Weekly Memory Data, number 1398, October 20, 2025. Gerald C. EclaireMD Foundation. Category, Methodology, Mission Statement. I write these medical papers not for fame or recognition, since I have already lived a long and successful life, though not always a healthy one. My purpose now is to share what I have learned about health, disease, and medicine, so that others can better understand their own conditions, prevent illness, and live longer, healthier lives. Preface. During from 1977 to 1980, while I was working in San Francisco, as a supervising engineer for the structural design of U.S. nuclear power plants and later serving as a research project manager at the Electric Power Research Institute, EPRI, in Palo Alto, California, I was also studying part-time at the Structural and Civil Engineering Department of the University of California, Berkeley, for 3 consecutive years. During that period, I took several advanced courses in stochastic design and structural reliability analysis. After completing that postgraduate academic training, I never applied what I had learned about stochastic modeling in my professional engineering career. However, following my recent stroke on June 21, 2025, I suddenly remembered both topology, which I studied 58 years ago at age 20, and stochastic methods, which I studied 48 years ago at age 30. As a result, I decided to apply these two mathematical tools, topology, mathematics, and stochastic analysis, statistics, to my ongoing medical research work. After spending some time refreshing my old knowledge base, I began conducting a probabilistic study on my biomedical subject of post-stroke memory recovery. I then wrote the following summary report. 1. Introduction and dataset description. This article presents a stochastic probability analysis of my memory recovery, following a hemorrhagic stroke on June 21, 2025. The purpose is to evaluate my post-stroke memory loss recovery patterns using probability theory, rather than purely viscoplastic energy, deterministic or geometric and data connectivity models such as my Viscoplastic Energy Theory, VMT, or Topological Data Analysis, TDA, frameworks. Each week included 7 sets of daily memory tests, and each set contained 20 memory testing items, giving 140 total trials per week, 7 times 20. The test length, format, and timing were identical throughout all 17 weeks, ensuring high comparability and measurement reliability. The dataset includes 1 output strain, memory test of percentage of correctness, and 5 input datasets. SBP, systolic blood pressure, PP, pulse pressure, HR, heart rate, sleep hours, and walking steps, each recorded daily for 7 days per week. These continuous and synchronized variables allow precise weekly averages that capture both physiological and behavioral changes associated with my neural recovery. 2. Theoretical framework of stochastic modeling. Stochastic analysis views recovery as a probability process, rather than a fixed deterministic outcome. In a biological sense, memory performance is influenced by complex and often random neural, vascular, and behavioral factors. This probabilistic framework quantifies uncertainty and stability during recovery. 2.1 Binomial representation. Each weekly memory test result can be modeled as a binomial process, where the probability of success, correct recall, is denoted by p, and each trial is independent. X approximately binomial, n is 140, p, where x is the number of correct recall items, and n is 140, is the total number of trials in 1 week. This representation is mathematically clean and realistic because each individual test item, correct or incorrect, can be viewed as a Bernoulli trial, and the weekly memory percentage is the ratio x per n. 2.2 Bayesian updating. Since the true recovery probability p is unknown, we assign a prior distribution and update it weekly with observed data. Assuming an uninformative prior beta, 1, 1, the posterior distribution of p becomes, from this posterior, the mean and variance of p are given by. This Bayesian framework allows the direct computation of probabilities that the true memory ability exceeds certain recovery thresholds. The criterion of sustained recovery is defined as p is greater than 0.95 maintained for 4 consecutive weeks. 2.3 Covariate linked model. To identify behavioral and physiological contributors, a logistic regression was applied to the weekly posterior mean probabilities using the 5 input variables. This hybrid design, Bayesian probability estimation combined with logistic covariate modeling, allows both quantification of uncertainty and identification of influential factors affecting recovery. 3. Analytical results. 3.1 Bayesian posterior findings. The posterior probabilities show a smooth and consistent transition from randomness to near certainty. The transition from uncertainty to stability occurred between weeks 6 and 9, especially weeks 7 and 8, when my memory test results reached almost 100%. From that point onward, the posterior distributions became sharply peaked, indicating high certainty of sustained recovery. 3.2 Logistic regression findings. The logistic regression confirmed the following standardized effects. McFadden R² is 0.17 means the model explains about 17% of the variation compared to a null model, indicating moderate fit. Breyer score is 0.068 means the predicted probabilities are close to actual outcomes, showing good accuracy. The walking activity, steps, remained the strongest behavioral correlate, though this observation was already visible by simple correlation inspection of the dataset, and my research results using both VMT and TDA models. 4. Discussion. 4.1 Interpretation of findings. The stochastic model confirms what visual inspection of my data already showed: a clear, monotonic rise in recovery probability, reaching full stability by week 9, 100% recovery rate, while stochastic modeling formalizes this transition through probability equations. My eye examination, results from both VMT and TDA, and my brain's natural intelligence of immediate pattern recognition, already drew the same conclusion much earlier. A reminder that natural human perception can often match computational inference. The shift from uncertainty to stability seen between weeks 6 and 9 demonstrates how neuroplastic reorganization gradually reaches equilibrium, where week-to-week fluctuations become minimal. 4.2 Strengths of stochastic modeling. 1. Quantifies uncertainty and shows confidence growth through data accumulation. 2. Provides mathematically clear probability thresholds for recovery, for example, 95% or more. 3. Integrates behavioral and physiological data into one probabilistic framework. 4. Validates consistency across weeks and confirms recovery stability. 4.3 Limitations and reflection. Although the stochastic framework is mathematically rigorous, it does not reveal insights that I have not already recognized through deterministic energy analysis and geometric analyses using both VMT and TDA models. The probability results and memory recovery curve confirm what my own intuitive reasoning, pattern recognition, and visual observation had already suggested. Moreover, this approach is computationally more complex, requiring several layers of Bayesian, updating, posterior integration, and regression modeling, yet the practical conclusions remain similar to those derived from my deterministic, energy-based, VMT, and geometric, TDA, methods. In short, this probability results and recovery curve validate the conclusions I had already reached through intuitive reasoning, pattern recognition, and visual observation using other deterministic research methods. 5. Comparative value to other models. Stochastic modeling aligns conceptually with my overall GH method, math physical medicine framework. It provides a probabilistic complement to the deterministic VMT and TDA approaches. However, it does not introduce fundamentally new insights beyond what I have already observed from those deterministic energy and geometric models. VMT quantifies the viscoplastic energy transformation during my stroke recovery, while TDA visualizes the geometric shape and data points, connectivity of manifolds. The stochastic modeling, by contrast, only assigns probabilities to what is already visible from the underlying patterns. In summary, stochastic modeling refines and confirms what has already been concluded by observation and deterministic analysis, rather than discovering new information. 6. Overall conclusion. 1. Each week contained 140 trials. 7 times 20, producing robust statistical evidence for weekly probability estimation. 2. The posterior probability of full recovery, P is 0.95 or greater, rose from near 0, 61%, at week 1 to nearly 10.999, 100%, by week 9. 3. Sustained recovery was achieved between week 7, 98.6%, to week 10, 100%, and maintained thereafter. 4. Walking activity showed the strongest behavioral correlation with memory recovery, a trend that was already visually apparent through other research methods, even before applying stochastic analysis. 5. The stochastic framework is theoretically sound, but offers little practical advantage beyond what VMT and TDA already show. 6. It does, however, provide an additional quantitative language to express certainty, suitable for publication or verification by other researchers. 7. This probabilistic model not only measures uncertainty with numbers, but also reflects what happens inside the brain during healing. As the weeks go by, small random changes in the brain's connections gradually settle into stable memory functions, showing how randomness turns into recovery, while stochastic modeling elegantly formalizes uncertainty reduction, my own observation, VMT energy results, and TDA topology. Geometric patterns had already led me to the same scientific conclusion earlier. The brain's intuitive pattern recognition and follow-on deterministic analysis, combined with mathematical reasoning, remains the most powerful diagnostic and predictive tool. This is one of my clearest methodological papers. It reflects my intellectual evolution, from mathematics through engineering, business, and medicine, and finally back to the mathematics I studied decades ago, now applied to my post-stroke biomedical recovery. The combination of personal history and technical precision gives this work both human and scientific depth. Although it stands as a complete study report, I do not plan to pursue further probabilistic studies in medicine unless they are absolutely necessary. 4 figure captions. Figure 1. Posterior probability of recovery, transition from uncertainty to stability. This figure illustrates the posterior probability P is 0.95 or greater, computed from Bayesian updating for each of the 17 observation weeks. The curve rises sharply between weeks 7 and 9, indicating the transition from uncertainty to stability in memory recovery. Posterior confidence exceeds 0.97 by week 7, and approaches 1.0 by week 9, marking full cognitive stabilization. Figure 2. Recovery phase diagram, memory percent versus week number. This diagram presents the observed weekly memory test results over 17 weeks, with each week containing 140 trials, 7 days times 20 tests per day. The shaded region, 90 to 99%, represents the uncertainty zone, where performance variability decreases as neuroplasticity progresses. Full recovery begins around week 5 at approximately 90% and becomes evident by weeks 7 to 8, when measured memory performance reaches 100% and remains stable thereafter. Figure 3. Logistic regression odds ratios. Influence of 5 behavioral and physiological variables. This horizontal bar chart shows the relative effects of the 5 weekly covariates on recovery probability. The shortest horizontal bar, steps, 5,000 per steps, exhibits the strongest association, confirming that higher walking activity corresponds to improved cognitive recovery. HR, heart rate, shows a moderate positive correlation, while SBP and PP have minimal influence within controlled ranges. Sleep hours have a mild negative effect, suggesting that excessive rest beyond 8 hours offers no additional benefit. Figure 4. Integrated Analytical Framework, VMT-TDA Stochastic Analysis. This conceptual diagram summarizes the GH method, Math Physical Medicine Framework. The deterministic Viscoplastic Energy Theory, VMT, quantifies system-level energy transformation. The geometric Topological Data Analysis, TDA, identifies spatial patterns and continuity, and the probabilistic stochastic modeling quantifies uncertainty and confidence in recovery. Together, these 3 analytical layers provide dynamic, geometric, and probabilistic insights into stroke recovery and neuroplastic adaptation. Disclaimer: this content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.